Alright, good morning everybody. In this lesson we'll be treating different operations you can carry out with vectors and matrices. So we'll begin with addition, subtraction, multiplication, and division, just like the way you have it in with numbers. You can also do similar operations with vectors since they are just arrays of numbers. So we can perform addition, subtraction, multiplication, and division. The multiplication, there are three types of multiplication that you can carry out with matrices. That's the scalar multiplication, um, matrix multiplication, and then element-wise multiplication. And we see all of them as we move on. So let's begin with addition. So let's create a vector 1 through 5, and vector 2 be, let's say, 6 through 10. Right. So one thing about addition and subtraction, and yeah, let's say addition and subtraction, is that the matrices that you are adding up or subtracting must be equal in dimension, right? So this vector and this vector must have the same dimensions. We use the size function, and the size. So you see that the number of rows and number of columns for both vectors must be equivalent for you to be able to carry out this addition or subtraction, right? So I can add these two vectors together. And what's going to happen is the elements in the corresponding positions are going to add up. So 1 will be added to 6, 2 to 7, 3 to 8, 4 to 9, 5 to 10. So you have 7, 9, 11, 13, 15, right? So that is addition. So vector 2 plus vector 1 will be the exact same thing. You can do vector 2 minus vector 1. So what's going to happen? This 1 will be subtracted from 6, 2 from 7, 3 from 8, 4 from 9, 5 from 10. Right, so all of them will give me 5. Right, but you can also subtract scalars. So vector 1 is 1, 2, 3, 4, 5. If I wanted to increment each number by, let's say, 10, 10 will be added to each element in the vector or the matrix. 10 plus 1 plus 2 plus 3 plus 4 plus 5. Right, all of them have been incremented by 10. You can also decrement by a scalar. That's a specific number as well. So this now means that you're subtracting 10 from each element in your vector, right? So that's addition and subtraction. So for addition and subtraction, if you're adding or subtracting two vectors, both of them must have the same dimensions so that there'll be no mismatch. And if you do it with scalars, the scalar will be added to um, each element in your vector or matrix. Okay, so let's now move on to multiplication. So let's say you have a vector. Let's just use vector 1 still. So vector 1, I want to multiply by a scalar. Right? So let's say by 10. So what this is going to do is it's going to multiply each element in my vector by 10. So it'll be 10, 20, 30, 40, 50. Right? Multiplied by fraction. Going to multiply each element by that fractional number. Right? So imagine now you had something like a vector of numbers, like 1 through 1000. You had this range of numbers and you wanted to do 3x plus 5. Right? If you were to plot this now, this 3 will multiply everything here. So you have from 3 to 3000, right, plus 5. So that will be your expression if you were plotting this out. Okay. So let's now go to So this is scalar multiplication. You're just multiplying by a scalar, and every element in your vector will be multiplied by that scalar. Right. So let's move on to matrix multiplication. So let vector 1 be let's use odd numbers from 1 to 10, and then vector 2 be let's do 15, 17, 19, 21, 23. This is what I want. No. Let's do 15 to 20. Okay, dimensions are 15 to 19. Alright. So for matrix multiplication, you must have that the number of rows of the first column must be equal to the number of columns of the first vector. Number of columns of the first vector must be equal to the number of rows in the second vector. Okay. So let me say it again. The number of columns in the first vector equal the number of rows in the second vector or matrix. Right. So this is what vector matrix multiplication looks like. You need to have two matrices or two vectors. Number of columns in the first one must equal the number of rows in the second one. If there are 3 columns in the first matrix, there must be 3 rows in the second matrix. If there are 4 here, there must be 4 here. Alright, so the number of columns here must match the number of rows here. Right? Because number of the, like for instance in this example, 10, 20, 30 will be transposed and they'll lie on, let's say like they'll lie on this first row here. So 10 and 1, 20 and 2, 30 and 3. So they'll multiply each other. 1 times 10, 2 times 20, 3 times 30. Just like you see here, and then you add everything up. And then you do the same thing for the second column. So the second column transpose and multiply with each of these numbers. 1 times 11, 2 times 21, 3 times 31. Then you add everything up. Excuse me, my battery doing that. Alright, then you add everything up. Then after you've done that, you go down now to the second row of the first matrix. So 10, 20, 30, transpose, multiply each element here. 4 times 10, 5 times 20, 6 times 30, and then you add everything up. And you do the same thing for the second column. So 4 times 11, 5 times 21, 6 times 31. Add everything up. Then you end up having 4 numbers. 1, 2, 3, 4. Right. So that's how matrix multiplication works. So if you had a different number of columns, a different matrix size, the number of columns must be equal to the number of rows for matrix multiplication to work. Now in our example here, we can't perform this because the number of columns in vector 1 is 5, and the number of rows in vector 2 is 1. So if we try this, dimensions do not agree. Right, incorrect dimensions for matrix multiplication, just as I said. Now what if we transposed vector 2? Now vector 2 has 5 columns. Vector 2 has 5 rows and vector 1 has 5 columns. Now this now would work. You'd have a 5 by 5 matrix. Why is it taking so long? Alright, 4, 4, 5. Okay, yeah, 4, 4, 5. You'd have only one element because you have only one vector and you have only one row and one column. So you end up having one number. So it didn't work the first time because the number of number of columns in vector 1 did not match the number of rows in vector 2. We'll see this better when we use matrices. So this is matrix multiplication or vector multiplication. You're multiplying the vectors together. The last multiplication is multiplication element-wise multiplication. Element-wise. So this
is element-wise multiplication. So if you have two matrices or two vectors, they must have the same dimensions for you to perform element-wise multiplication, meaning that if this was a 2 by 2 matrix, the second one must also be a 2 by 2 matrix. The matrix dimensions must match each other. Now, here, for this element-wise multiplication, this one here, or in the first matrix, the elements in the first matrix multiply their corresponding elements in the second matrix. So 1 here multiplies 3, 7 will multiply 3, 2 will multiply this 5, 4 will multiply this 2, right? So they look for their corresponding elements, and then they multiply each other. So vector 1, vector 2. Now vector 2 is now, we need to convert it back to the row vector. This is vector 1. You can see that the dimensions match each other. This is 1 by 5, this is 1 by 5. So vector 1 and vector 2. Now remember, the asterisk here is for multiplication, and since these are two vectors, you're performing matrix multiplication. In order for you to perform element-wise multiplication, you need to add a dot right here. So the operator for element-wise multiplication is dot asterisk, meaning that you want this to be element-wise. So that 1 here will multiply 15, 3 here will multiply 16, 5, 17, 7, 18, and 9, 19. So that's what happens here. So this times this, this times this, this times this. But this is element-wise operation, multiplication, sorry. So this is the operator for element-wise multiplication. You want the corresponding elements in both matrices or vectors to multiply each other. So that is element-wise multiplication. Let's try it again with something else. Let's say vector 3 be 1, 2, 3, 4, 5, 6, and then vector 4 be 10, 20, 30, 40, 50, 60. Vector 3 dot times vector 4. Right, so 1 times 10, 2 times 20, 3 times 30, 4 times 40, 5 times 50, 6 times 60. Okay. Alright, so this is multiplication. Now, onto division. Now, for division, we can perform scalar division. So you just divide by a scalar. So this is vector 4, you have divided everything here by 10. Okay. This is vector 4, you're dividing everything by 10 or by whatever number, and each element will be divided by that number. Like just like multiplication, addition, and subtraction with scalars. Alright, then we can divide vector 4. This is vector 3. We can perform element-wise division. So each element here would be divided by each element here. So this is element-wise, meaning 10 will divide 1, 20 over 2, 30 over 3, 40 over 4, 50 over 5. So you have 10, 10, 10, 10 all group. So what if you are dividing one fraction by another? Oh, sorry, one vector by another one. Alright, so for division, then for the two matrices, you must have that the number of columns of the first matrix must be equal to the number of rows of the second matrix. Right, so I have an example here. So we define A as this a 3 by 3 matrix, B as a 3 by 3, another 3 by 3 matrix. Number of rows must be equal to number of columns here must be equal to number of rows here. So our x now will be can be B divided by A, and because the number of columns is equal to number of rows, the division would be carried out successfully. There will be no dimension mismatch.